Hi! In this short video, let's take a look at semiconductor curve tracing with the help of function generators or arbitrary waveform generators. By now, everyone is probably familiar with the characteristic curves of transistors and MOSFETs. These IV curves are useful not only for educational purpose, but also for understanding the operational characteristics of these semiconductor components. In the good old days, when choosing the output transistors or MOSFETs for Class B amplifiers, for example, curve tracers were commonly used to ensure that the parameters of these output pairs are closely matched to reduce signal distortions. The idea behind a curve tracer is fairly simple. For instance, when measuring the collector-emitter voltage versus collector current characteristics, we can step through a few pre-configured base current settings and then use a triangular wave or sawtooth wave to sweep the collector under these different base currents. The resulting curve is the familiar VCE versus IC curve. Now, building a curve tracer is actually not particularly difficult. I built one many years ago using a mixture of analog and digital ICs and obtained some very promising results. For those who are interested, you can check out the link in the description below. But for the purpose of this video though, we're going to take a look at obtaining these curves using function generators and AWGs we may already have. And we'll talk about some of the limitations and nuances in the process. Here is a simplified schematics showing you how a curve tracer is typically done. If you take a look, you will see that the choice of the ground is a little bit unusual here. The ground reference is placed at the emitter, not at the bottom of the R1 here. This is because the different channels in an oscilloscope share a common ground. Therefore, we have to compromise the ground point in order to measure both the VCE and the current flowing through the transistor here. As you also notice, technically speaking, we're actually measuring the IE, not IC. But since the gain of a transistor is fairly large, the current difference between the IE and IC are pretty minute, so most of the time this difference can be ignored. The grounding situation here actually introduces another problem. In this case, the waveform driving both the base and the collector emitter, they have to stay afloat, as otherwise they will short out R1 here, so this tracer will not work. This means whatever signal source we use, we have to have isolated grounds for the different channels driving these two waveforms. Now, unfortunately, most of the cheap multi-channel AWGs do not have isolated grounds, so you will have to use multiple of them as independent signal sources. Actually, what I just said was not entirely accurate. As long as the signal generator's output is isolated from the earth ground, we can use this modified circuit to generate the curves. Now, the only major change here is that the placement of R1. If you look at the original design and this new design, you will see that R1, instead of being on the emitter side, now is on the collector side. So the benefit of this alternative circuit is that you can use a single channel generator to generate both the base and collector signals, as both signals are referenced with respect to the emitter itself. And the probe's grounds are tied to the collector instead of on the emitter in our original approach. Another benefit you can see here is that the collector current being measured here is the actual collector current that is flowing through R1, whereas in our original design, that collector current we are measuring is actually the emitter current flowing through R1 down at the emitter side. Although the difference introduced is quite small, given the large current gain of the transistor. Now, the major downside with this alternative approach is that because the VCE measurement is negative with respect to the oscilloscope ground, the generated image is mirrored along the y-axis, which makes the resulting image less conventional, as you typically cannot flip the image along the y-axis on an oscilloscope. With the approach we mentioned earlier, you can see that the current measurement for IC is actually negative with respect to the oscilloscope ground, But on most of the scopes, you can easily flip the verticals so that the resulting image looks the way you expect it to be. Anyway, for the rest of the video, I will stick to my original approach as shown here, as I have more control over each of the signal source and can adjust the offset of each very easily. And towards the end, I will show you briefly what the curve looks like using the alternative approach. Now with these limitations in mind, let me use my UTG 962E and the 2D72 to generate these required waveforms and hook up an oscilloscope and see what we got. By the way, it will get rather messy after I hook up the probes, so I thought I would just show you what I have currently on the breadboard here. So the transistor is a 2N3904 small signal transistor, that is an NPN. Transistor is quite common. And the resistor here at the emitter is a 1 kilo ohm, and the one on the base is a 47 kilo ohm resistor. I have now set up these two signal generators to drive the transistor testing circuitry here. And I'm using these standard oscilloscope probes. Let's just quickly verify the circuit setup here. This set of leads comes from the 2D72 signal generator, and you can see here the ground clip right now is connected directly with the emitter of the transistor. Now it's a little bit hard to see, but I just want to kind of show everything here so that you kind of understand the overall picture. And if you do need to reference, you can always refer to the schematics I mentioned earlier. Now, the positive input goes through this base resistor, which is a 47 kilo ohm, and it goes to the base. So that completes the base driving circuitry with this staircase waveform. The sawtooth signal generated by the UTG 962 goes to sweep the collector and emitter. As you can see here, the output is this leads, and you can see indeed the ground ties to the bottom of that emitter resistor that we mentioned earlier, and the positive goes to the collector directly. The scope leads from both channels are grounded at the emitter here, as you can see. And the channel 1 is also tied to the collector, so that measures the VCE, whereas channel 2 is connected at the bottom of that resistor R1, as we saw earlier, to monitor the current flowing through the collector and emitter. Now let me turn the scope into XY mode, and we'll enable the output from both of these generators, and we'll see what we got on the scope. You can see that if I zoom it in, that the result is actually not bad at all. Of course, the choice of the base resistor and the emitter resistor are actually not arbitrary. They're chosen so to ensure the best results for the given capabilities of our signal generators. So let's take a close look at what our current outputs are from these signal generators. One thing I wanted to point out, which is important in generating a stable image, are the choice of the frequencies of these two waveforms. Because we're using two independent signal generators, the clocks of each one essentially are running independent of each other. So in order for the display to be stable, you really don't want the frequencies of these two generators to be the multiples of each other. If we take a look at the frequency setup here on the 962E, you will see that currently we set it at 1 kilohertz, and the signal output from the Handtech is currently set at 984 hertz. This ensures that these two frequencies do not generate a beat. Otherwise, you will not get a very nice looking image, as I will show here. So let me, for instance, if we increase the frequency of this staircase signal, and let's actually go down. If we are getting closer to that 1 kilohertz, you will see that we will be generating a beat, which makes it very hard to see. And at exactly 1 kilohertz, basically the generated image is actually not quite legible here. So we will make sure that these two frequencies are as far apart as possible and not the integer multiples of each other. One of the limitations of using a signal generator to sweep the emitter and collector voltage is that the output from the signal generator is generally very limited. And in this case, when we're generating a single-ended output from 0 volts to 10 volts, we have to set an offset of 5 volts. So the overall amplitude is only 10 volts. But if we're choosing a symmetric output, if you, for example, let's do the amplitude. If we do a offset with 0 volts, and we can actually generate an amplitude of 20 volts. So now you can see we have some breakdown in the reverse side happening, and you can clearly see that on the curve tracer here. So that is pretty cool. Now let me change the generator output to 0 to 10 volts again to concentrate on the positive side. So let's change the amplitude to 10 volts and change the offset to 5 volts. So again, now we're looking at 0 to 10 volts. Of course, if we change the base resistor value, we will get a different set of curves. So right now the base resistor is at 46 kilo ohm. So let's put in a 10 kilo ohm resistor and see what we got here. So let me switch this to the 10 kilo ohm. Of course, now the y-axis is out of the range. So let's turn it back down a little bit. And as you can see, now we have a different set of characteristic curves. With this 10 kilo ohm of base resistor and 1 kilo ohm of emitter resistor, we found ourselves do not have enough VCE dynamic range to extend the upper portion of the graph. Of course, in this case, you can do something a little bit clever because we know that the UT962E can actually generate a 20 volts peak-to-peak signal. So we will come back here to generate that 20 volts peak to peak. So of course right now with the offset of 5 volts we cannot do that. We will change the offset to 0, and now we change the amplitude back to 20 volts. But the problem right now is we cannot utilize the negative 10 volts. So to utilize that, what I'm going to do is to add a DC offset to this signal here. So for that, I'm going to turn on the power supply and generate a 10 volts, which is what is currently outputting. And I'm going to put it on top of this output from the signal generator here. So instead of generating minus 10 volts to 10 volts, I'm going to lift it up by 10 volts. So now the resulting curve is actually from 0 to 20 volts. As you can see, now we have a much better curve as compared to before. And let me just adjust it a little bit more so you can see it better. Of course, to do some quantitative analysis, you can turn on the cursors on the scope and do some measurements there. And of course, we can use the same setup to measure the characteristic curves of a MOSFET. And now on that breadboard, I swapped out our 2N3904 with a 2N7000 MOSFET. And you can see that we have a different set of curves being shown here. Unfortunately, as you can see on the scope here, we only have a few lines there. That's because we have some limitations on the output voltage from the Handtech signal generator. Right now you can see that the amplitude output is pegged at 2.5 volts, and that's actually the maximum we can generate from this signal generator. And if we reduce that output, you can see that we have even fewer lines to work with. So that is the limitation of this signal generator. Of course, the same setup can be used to measure PNP transistors and P-channel MOSFETs as well. All you need to do is just swap the input signal's polarities. Just for completeness, here is the setup of the alternative method that I mentioned earlier with the 2N3904 under test. And you can see what I meant by that image is flipped. But the benefit is that you can use just one dual channel waveform generator for both waveforms. And that pretty much concludes today's video. I hope you enjoyed the video and learned something new. Don't forget to give it a big thumbs up and remember to subscribe to this channel for more videos like this in the future. I will catch up the next time.